recap, I think we left off where we are just about getting down to the analysis of the rectangular orthogonal rectangular range searching in 2 dimensions, right. So let me just see. So where did we leave off? So we were left off at a point. Okay, let's see. Right. So I think I just proposed the result, or I just advertised the result. We didn't really prove it, right? So reporting range query for orthogonal rectangles. Take order. Steps. Well, actually 2D tree in 2 dimensions, right. So any question about the basic scheme before we do the analysis, the query tree? Yeah, it's very simple. So just as a recap, what did we do? We alternately sort of sliced the plane using a median on the x coordinates and then a median on the y coordinates, and we obtained smaller and smaller rectangles. And then when we queried when the query rectangle came along, we only found out that the tree was defined by this partition. So the root of the tree defines the entire plane, or basically a bounded box which contains all the points, and the 2 children correspond to the left and the right half. Then the children of that basically correspond to the up and down, and then from this point onwards recursively we build the data structure for the four quadrants, well, whatever the 4 partitions that we have obtained so far. And then when the query rectangle comes along, we start from the root, and then we take care, first query the simple cases. Does it completely contain the region defined by the node? If so, then you stop and report all the points. Does it have does it basically have no overlap with the region? Then again you just end your range search, saying that no, sorry, there are no points to reported. The only case where you actually continue down is when there is some kind of partial overlap with the regions, right. So that's how this range query proceeds. And so how do we do the analysis? You can actually, because the search tree is itself defined recursively, you can try to write a recurrence for the query time, right. So suppose Q of n is the worst case query time. So query time in this case, query time basically means the number of nodes that we visit along the way till the search terminates completely, right. Number of nodes visited, because every time we visit a node, we are basically doing some constant kind of operations to find out whether it's a partial overlap, no overlap, or complete overlap, right. Points, and we basically want to write Q's of n as something, right. So the rectangle comes along, okay. So what we'll do is, to simplify the analysis, we will actually look at in the following way. You look at the 4 boundaries of the rectangle, okay, the 2 vertical boundaries and the 2 horizontal boundaries, okay, and we'll actually compute the number of intersections with a vertical line, analogously a horizontal line, okay, with the number of regions in the tree. See, this partitioning basically I didn't continue further, but essentially within each of these, okay, you again have regions, right. So, you are basically subdividing into finer and finer rectangular regions. So, I am going to compute the number of times, let us say this edge, okay, not number of times, but the number of regions that this edge intersects with, okay. And then analogously this will also intersect with the maximum number of that many regions. And so, if I multiply the number of intersecting regions of this vertical boundary, I will multiply that by 4 and that will give me the maximum number of nodes visited. Do you agree with that? Okay. Let us try again. So, I am trying to find out how many. So, as we proceed along this search tree, it could actually from a node actually visit both its children, right. It is possible, right. So, in the end, we are going to basically look at what is the total number of, okay, so if I look at the tree, just the abstract tree, here is my KD tree, okay, this is a green tree, okay, not a red tree. Okay. So, in the end, these are the leaf nodes, okay. As we move down, okay, it is possible that the rectangle could actually intersect both these and both of these, but what we are trying to analyze is that eventually it is not going to visit all the leaf nodes, but it will visit only a maximum of some subset of these leaf nodes, right. So, some search path will end here, some search path will end here, so on and so forth, right. And to find out how many nodes we visit, okay, I will try to analyze that using not looking at the entire rectangle, but looking at an edge of the rectangle. Okay. So, the maximum, and each of these correspond to rectangular region. There is some rectangular region that corresponds to this, right, some rectangular region. Each node is a rectangular region. So, maximum number of rectangular regions intersected by and let us say this edge by the left boundary. Okay. Do not confuse between the range and these rectangular regions. This is the edge, the left boundary of the range, the rectangular range. So, I will find out how many of these rectangular regions, or in other words, how many of these nodes, okay, this left edge, okay, can visit, and then I multiply that by that 4, and that will give me the maximum number of nodes this rectangle can visit in the course of this search process. We are trying to find out how many of these rectangular regions this range can overlap with, okay, which means that at least one of the edges should be overlapping with that. So, now I am trying to find out for each edge what is the maximum number of rectangular regions that this edge can intersect, and in the end if I multiply that by 4, that will certainly be an upper bound on the number of nodes this range can actually visit. At least one of the edges must be intersecting the rectangular region, otherwise there is no overlap. We are counting the number of partial overlap. Okay. So, I am counting the number of partial overlaps by first looking at a single edge, and I multiply that by 4. Okay. All right. So, when I am writing this this recurrence actually will correspond to the number of rectangular regions an edge intersects. Okay. Where the rectangular region contains endpoints. Okay. So, that is what Qs of n denotes. So, the actual number of nodes that we can visit during the course of this range query is this Qs of n, maybe I should call it Q prime, okay, to distinguish it from the skews of n. Okay. This is for the rectangle, this is for an edge of the rectangle. And so, the claim is that q's of n will be no more than 4 times q bar of q prime of n. Okay. So, I will focus on writing a recurrence for the q prime of n. And I claim that this can be bounded by 2 times q prime of n over 4 plus 2. Can we justify this? Let me put down the figure again. Okay. So, let us say we are talking about this particular edge. Right. Now, it will this recurrence depends on how this tree is defined, whether the first node bisects the x coordinates or bisects the y coordinates. Okay. Let us assume that this one, the root node, okay, bisects the well, in this case it is the bisects the x coordinate. Okay. So, fine. Now, it bisects the x coordinate, I am talking about this edge, okay, and there is some overall boundary of this region that contains endpoints. So, as we proceed down the tree, when we get to this level, that is, we skip this level and go to the next level, we are back again to the same situation that these nodes are bisectors of x. This is bisector of x and this is bisector of x. These nodes are bisectors of y's. Okay. So, when we proceed down to this level, again they correspond to rectangular regions which have at most how many points? N over 4, right, because we split twice. We split along y and then back to x, right. So, split it once, these are n over 2, n over 2, and then again these are split again into 2 halves. So, these correspond to n over 4 nodes each. So, these rectangular region correspond to n over 4 nodes, n over 4 points. Right. So, how many of these regions can this intersect? The left edge. You see that? So, it is going to be either to the left or the right of this vertical line. Okay. So, it is going to intersect at most 2 of these regions which have n over 4 points. Okay. And plus, of course, I have already 2 intersections because it intersects this rectangular region and this rectangular region. That is why I have added 2. So, I have added 2 because this edge intersects region 4 and region 3 plus recursively whatever it intersects within these regions, that is 2 times q prime of n over 4. And so, what is the solution to this? Are you convinced about the recurrence? Okay. So, now just solve this. Okay, solve it later maybe. So, I claim this is basically square root of n. The additive constant is not going to make too much of a difference, and you have to write the base case and so on and so forth. Okay. So, that is how you get square root of n. Fine. So, that is basically your 2D trees, and in general maybe you want to guess again, what do you think will be the result if we talk about k dimensions? So, the KD tree is for k dimensional range search. So, query time in, let us say, k dimension for n points, what do you think it should be? For 2 we know the answer to be square root of n. Well, an exercise for you again. oh sorry, k, not d. Okay. So, you may want to just test your understanding by writing the recurrence and solving it. And so, but then if you observe this bound, as k gets bigger, this actually becomes closer and closer to n, right. K becomes bigger, basically this becomes close to n. Okay. How much is the space? Let us say space for 2-dimensional KD trees. So, in the way we are answering the query, what is implicit? I mean, how do we actually answer the query? Depends on that, the space will depend on that. So, are we going to store all the points in each of the internal nodes? Yes or no? We do not need to, right? The moment we discover that, suppose this entire node is contained within this region, okay, we can maintain pointers where to all the leaf nodes of the tree rooted at this node, we simply list them out, that is all. So, I do not need to store explicitly with each node the points associated with that rectangular region. The moment I know that this rectangle contains this region, okay, then I am going to list out all the points that are with the leaf nodes of the tree rooted here. Okay. So, each point is stored exactly once actually. So, it is a very powerful property. So, the KD tree has a property that a point is stored exactly once. It is not even order of once, it is exactly once. Okay. So, but there are some pointers, of course, the tree has a pointer structure because the primary tree has a structure, and then for each of these nodes we maintain certain pointers. But as far as points are concerned, they are stored exactly once. Okay. So, I will just write order n, okay, for 2-dimensional. Okay. And what do you think about k dimensional? What changes? K by 2. No, how can the space be sublinear? The space has to be at least the number of points, right? You mean k times n? Okay. What I will let you do is figure out how actually you are going to design this KD tree. So maybe there is some kind of recursion that you need to understand before you can actually guess what this is. But yes, it is not going to be more than linear, whether it is k times n or order n, that is something I want you to figure out. Is it k n or order n? So, the question is that is a point. So, here a point is stored exactly once. Do you need to store a point more than once? I mean, the basic methodology that we have developed, why should we store a point more than once? I mean, if you follow the same strategy that let us say in 3 dimension a cube may be completely contained within, and I am just simply going to list out something. But then there is a catch that we are dealing with higher dimensions. So, maybe there will be some kind of nested structure within each of these nodes. Okay. So, there is this something for you to consider. It is not immediately obvious, or maybe not, right? Maybe just a simple structure, same thing. If there is a partial overlap, we go and search this entire structure, and if there is no overlap, we do not search that subtree. If there is complete overlap, we list out all the nodes in the subtree, all the points in the subtree. So, just give it some thought whether it should be exactly once or it is something more complicated. No, I am not ignoring it that way. I am just saying that the points are stored exactly once, okay, and certainly the number of pointers do not exceed O of n, because the tree has size at most n leaves, and each node is going to have a couple of pointers. See, the points are something that could occupy a lot of storage depending on what you store with a point. No, but each node will have only constant number of pointers, right? And if there are order n number of nodes, there will be order n number of pointers.
Sir, but points in 2 dimensions are stored in a particular order. You are saying that the pointers are such that they start from one location and end at one, and you list the entire points.
So it doesn't matter in which order I list out the points. I know that if this node is completely contained in the rectangle, all the nodes in the subtree have to be listed. It doesn't matter in which order I list them. There is no obligation to list them out in a certain order.
Shouldn't it be at least, I mean, there are n leaf nodes, and every leaf node has size k. So
Every leaf node has size k. Why do you think every leaf node has size k? It's k dimensional. The points have k coordinates. That's all. See, the points here. So here is where basically in our model we assume that we don't care about the number of bits, etc., whatever. So a point is a point, a real number. That's all. So it is not. I mean, this model certainly doesn't take care of bits and things like that. We are looking at basically a real number as a real number. That's all. So this is a deficiency of this entire model, but then we have lived with it and we are going to sort of live with it, and we are not going to divert from this model. So the question is, each data point is stored exactly once. That's all. Now how much space each point occupies, that we don't know. What kind of storage we are assigning to a real number. Right. So and it is only under this assumption. So yesterday I stated a result, and I was not I was not very precise about it. So I said that this square root of n bound is the best possible for order n space. So actually it is not order n space. The square root of n bound is the best possible if you store a point exactly once. If you order n space, you can actually get better bounds. Okay, so I will leave that as an exercise, or I'll properly formulate that when you should be able to. As we go on, we'll cover more material, so we'll see how we can improve on that. Keeping the space big of n, but there is no guarantee that a point will be stored exactly once. A point may be stored more than once, maybe 3 times, 4 times, 10 times. Okay. So the pointers are only associated with the data structure. Okay. The points are the input data points. So there is a distinction between the nodes, the pointers, and the data points. The data points are real numbers, and these are whatever your words or your nodes, pointers. Right. Okay, so the obvious question here is that can we improve? So the space with order n, let's say, even if a point is stored more than once or some constant number of times, it's still order of n, big O of n. Okay. So we can't do much better in terms of space. In fact, in the case of KD trees, we have stored a point exactly once. We can't do anything better than that. But can we improve on the query time, basically? So that's square root of n plus, right? So it's square root of n. So square root of n is the number of nodes visited. Okay, let me go back again. Square root of n is the number of nodes visited, and of course we also have to report all the points. So I may not proceed further along a node because this node is completely contained inside. Okay, but I have to still list out all the points. Okay, and the points are being listed out exactly once. So therefore, the overall reporting time. The overall report time is square root of n plus k, where k, I should not use k because I am using it somewhere else. So let us say m, where m is the output size. So also a point is reported exactly once, because the nodes are actually disjoint, the regions are completely disjoint. So I am reporting a point exactly once only when we conclude that here this entire region is contained within the range. So square root of n is the number of nodes visited of the KD tree, and each point is reported exactly once. So the total running time, query time, is square root of n plus m. The second part you can't do anything about, because that's your output size. Okay. So the question is, can we improve on this? The square root of n does appear to be quite large.
But you said that if you represent the point
Exactly once, this is a lower bound. Yes.
So then how do you
but I may be able to use some big O of n space. Why should I be restricted to using storing a point exactly once? Maybe I want to store it twice or thrice or 4 times or 10 times. So, this bound does not apply when it is stored more than once. Okay. So, can we improve on this square root of n bound? Okay. It is also possible that to improve on the square root of n bound, okay, there may be some kind of a trade off in space. Okay. Perhaps space has to increase. So, in general intuitively you can we have actually seen some examples in this course itself, that if you want to speed up your queries, okay, you may actually have a rather wasteful data structure. Okay. Think about you remember we did this ray shooting thing, where we had the segments, we chopped them into trapezoids and we drew these vertical slabs, and we noticed that if we can do this kind of ray shooting or point location using just 2 binary searches, once along find out which slab contains this and within a slab where it is contained. So, that was exactly like 2 log n, right, 2 binary searches. Problem was the storage. The storage was was blowing up to something like quadratic. Of course, we had other mechanisms to improve the storage. So, but intuitively it should be clear that if we allow more storage, it may be possible to actually improve the query time. So, there is an inherent, okay, sometimes there is an inherent space time trade off, but these are very difficult to establish, because we are talking here about lower bounds, right. It only makes sense to say that so there may be some kind of inherent space time trade offs, but the space time trade offs must be some kind of lower bound, okay, must be lower bounds. Only then you can claim that if I use less than 5 times n space, I have to use at least so much of query. I need at least, my query time will be at least so much. So again, these are rather hard, but then there are actually some really very deep and beautiful results, okay, which we are not going to get into, but I will probably mention it on the way what kind of bounds are known. Okay. So, right now let me look at a slight variation of this 2-dimensional range query problem. Okay. I will relax the problem, okay, and develop a slightly different method. So, instead of rectangles, let us look at some kind of slabs. Okay. So, here are points. Okay. And my queries are vertical slabs. Vertical slabs essentially means that their ranges are of the form. So, the family of ranges is x1, x2 Cartesian product with minus infinity plus infinity. So, in the y direction, I am willing to come to look at the entire slab. Of course, this minus infinity plus infinity is actually bounded because the points are enclosed within a box. Okay. So, minus infinity plus infinity only means that the extent of the y coordinates. Right. So, if I pose this kind of a range query problem, how would you solve it? So, it becomes a one-dimensional problem. Basically, what you are saying is that, well, this problem is effectively a one-dimensional problem, because I can project all the points in the x direction and simply use my my earlier solution, okay, optimal solution, log n query time, order n space, and log n preprocessing time. Okay, great. Okay, so let me then make the problem a little bit more difficult. Okay, so how about a three-sided kind of a query? Right? So, it is bounded on 3 sides, but not on the 4th side. You can have two trees. And then how do you find the intersection? The moment you have two trees, so that I'll tell you. So in general, the problem with that kind of approach is that you are going to. So I am going to solve the problem in x direction. I am going to solve the problem in y direction, and somehow combine the results. Okay, but then what could happen is that I may overcount. I may just overspend a lot of time figuring out. Let us say in the y direction, if this was bounded here, I will still in the x direction I will report all these points, and then I have to find the intersection. But in the meantime, I have already done the work of identifying all those points because I am reporting those points. Okay. So, doing this solving the problem somewhat in an uncorrelated manner, okay, will not get us the optimal results. We will lose that. Okay. So, we can't afford to ignore one axis and solve it independently on the two axes. Right. So, that is not going to work. But there should be some way of combining the two searches. That's the bottom line. So even before I take up this problem, let me discuss another thing. So for the moment, I will actually ignore that I have this boundary, okay. And so we are back to the minus infinity plus infinity, and we are back to the one dimensional problem, but I will actually now view the one dimensional problem slightly differently. Okay. So if you recall, I mean, I started by saying or at least introducing the range searching mechanism as partitioning points in a certain way, and then we find out, and we build a tree on these partitions, and then this range with this range we find out which of these partitions it intersects partially, in which case we recursively search. If it does not intersect, we do not search. If it completely contains inside, we report the points. Okay. But when we did the one dimensional solution, we were not really using this structure, right. We did not have the structure in mind. That was a natural solution. You knew about binary search, find the left end points, keep walking till you hit the right point and be done with it. So we certainly did not think in terms of any kind of partitioning of the points. Okay. And in many contexts, these partitionings, there are some special partitioning like we did in the case of KD trees. We defined some special kind of partitioning based on the median and things like that, right. So we actually came out with a family of something like order n rectangular regions. If you think about it, the first time we partitioned, we got 2 rectangles, then it was 4. So so as we move down the tree, it's a geometric series, 2 plus 4 plus 8, eventually you can't have more than n rectangles. So you actually, from a set of n points, we define a set of about order n partitions, okay. And these are often referred to as, when there is a special kind of partitioning, they are called canonical partitions. So when we devise a solution, these partitions are not some arbitrary partition or arbitrary clustering. Surely, it must have something to do with the efficiency that we expect out of it, how efficient the query time should be, how efficient the search should be, and so on and so forth. Sorry, the space should be, and so on and so forth. So they are not arbitrary partitions. Okay. So they are some special kind of partitions that we cleverly design. Okay. Like in the case of KD trees, we designed these rectangular partitions. Okay. So now let's go back to the one dimensional problem. We didn't solve the problem using any kind of this partitioning technique. Okay. So let's revisit that problem. So what kind of partitioning do you think would be appropriate for this? If you want to solve it like a general range query problem. Ranges are intervals. Okay, fine. That's a very natural one. Good. Right. So maybe at the first level, we partition like this. Okay. So we have a node that corresponds to the entire set of points, okay, and then we have these 2 nodes that corresponds to the left half and this to the right half, right. And then you continue like that. You again find the median of this. Okay, you just continue like that, right, and you have about depth of log n. Each node again is associated with a partition, right. So, this at level 1, okay, there are 2 partitions, okay. So, left and right, and then again maybe you call it LL and LR and RL and RR or something, right. So, then you have these LL, LR, RL. Right. So, you can have label each of these points and say again this one is associated with this left set of n over 2 points, this is associated with n over 2 points and so forth. So, this becomes your becomes basically a 1D tree. So, KD tree we started with a 2D tree actually without even bothering about the 1D tree, but this essentially is the 1D tree of the KD tree. So, you are going to again look upon this search process as given any arbitrary interval, what do? You find out is this interval basically has a non-empty intersection with this half and this half. In that case you proceed along both, okay, like here, and so on and so forth. So, can you quickly analyze how many nodes we will end up visiting in this 1D tree? So, I have modified my 1-dimensional search, right. I have built a 1D tree which is the 1-dimensional KD tree, right, and I am searching using the same principle. I have given any arbitrary interval, okay, I will see whether it has non-empty intersection, if it is completely overlaps, then of course I do not have to search further, I can report all the points. If it has no intersection, I do not go down that branch. If it has partial intersection, I have to go down both branches. Okay, so that is a great improvement, right. From square root of n you are 2 log n. Why could you guess that, or why could you conclude that so quickly? Because it has some similarity to that segment trees that we did before, right. So, you can argue that at the forking node, after that you have some very ordered sequence of nodes that you are going to visit, and at each level you are not going to have more than 2 nodes basically that you are going to visit, right. So, your overall number, so your search time is actually just log n, and of course, the reporting time is whatever the number of output points are there. So, this gives immediately, this leads to a query time of order log n plus output size. Okay. So, the 1D tree is actually quite efficient. So, why are we doing all this? Well, let us not go to k dimension, we are going to look at only 2 dimensions. Okay. So, remember this picture. So, finally, what is happening? Okay, one thing that we are getting out of all this is that any interval, any arbitrary interval basically can be expressed as a union of, that is basically the what we have done here. Okay. So, this interval any arbitrary, so any arbitrary interval, maybe I should write it down here. Okay. So, build a 1-dimensional KD tree, okay, and observation is that any arbitrary interval x1 x2 can be written as a union of, I will leave that blank, disjoint, well, these are canonical intervals, right. So, I will just mention this as canonical intervals. Okay. So, what is this figure? 2 log n, great. Okay. Let us go back to this picture. still this is a one dimensional problem, okay, but now we are viewing it as something like this particular interval x1 x2 okay, can be expressed as a union of some disjoint intervals, at most 2 log n intervals, right. So, maybe it is one interval is like this, another interval is like this, some disjoint intervals, and these are a maximum of 2 log n, 2 log n canonical intervals. Okay. Fine. Now, what I do is I again go back y 1 y 2. How can we now answer a query, a 2 dimensional query? Sort all the points in each interval and right. So, this 2D interval now it is y 1 y 2. Okay. So, I have defined some y 1 y 2. So, let us say this is y 1 and this is y 2. Okay. Again this entire region can be expressed as union of this plus this plus this plus this disjoint intervals. Each of these intervals, the entire vertical slab okay, contains many points that may not be inside the y 1 y 2 range. But then what I can do is within each of these intervals I can build a data structure for one dimensional search along y direction.
Sir, but is it also not stripping off one dimension first and then introducing the second dimension? I mean that's what you said that we should avoid.
No, no, no. So, yeah, so we are not doing it. So, what we have done is that we have done it very cleverly, right. We have actually not done it for all the points, we have done it for these canonical intervals. Yes. So, we have done it only for the canonical interval. Yeah, we will see that, we will see that. Sure, I mean that is a good point, but we will quickly come to that. But even before that, I hope that you are following how the query is going to look like. So, I do the one dimensional query, I mean, so well, it is like a one dimensional query where you are finding out which canonical intervals are spanned by the x1 x2, and that is a set of at most 2 log n disjoint intervals. Okay. Now, once we find out that these are the intervals, within each interval I do a one dimensional search, and each one dimensional search will cost me log n plus the number of points reported, log n plus number of points reported. So, within this interval, now it is just a y 1 y 2 interval, whatever points are there, suppose there are k 1 points here, there are k 2 points here and k 3 points here, this will cost me log n plus k 1, this will cost me log n plus k 2, and eventually when you sum it up, what do you get? You get basically log n at most log n times, okay, plus basically k I, which is k. So, you get a order log square n plus k query bound. So, query time you immediately get an improvement from square root of n to log square of n all the way down, you know. So, then boom, it's an exponential improvement actually, square root of n to log square of n. Of course, it is log square n, not log n. Log n would have been even better. Right. So, we will struggle a little bit more with that. What is the space bound? Someone brought out a very good point. What is the space bound?
Here, is it that for each of the, so I have a tree on the x direction, I mean the, because we are dividing.
Okay.
For each of the node, am I
yes, yes. So,
for
let
the y direction for each of
yes, yes, sure. So, let me put up this picture again. Right. So, this tree, the primary tree, so there is a primary tree and a data structure actually within each node. Okay, let get a little bit more details. So, the primary tree is on the x points, it is a projection of the points on the x axis. Okay. But then within each node, okay, so this node basically represents all these points. These points also have a x coordinate, which I have completely ignored here. So, within this I am going to store the one dimensional data structure on y coordinates. That takes linear time, right? The space will be linear space. So, for all these n over 2 points, so n over 2 points will be stored here and n over 2 points will be stored here, where there is a data structure. So, within each node there is a secondary data structure for the searching in the y direction. Okay. Similarly, for each of these nodes there is a data structure on n over 4 points on the y direction. Right. Now, when you add it up, you see that every level has basically a size n. So, it is blowing up. So, space is n log n. So, we have blown up the space. Does not look very serious. I mean, a logarithmic factor at the, and what you are getting benefited by is from square root of n, you come down to log square of n. Right. So, it does not appear serious for theoreticians, okay, but you know, the real world people, they will really scream, you know, no way, you know, I am storing gigabytes, I am not going to store, you know, another whatever 30 times this. That is what comes down to, right, log of n of a gigabyte. So, for them 30, and for anyone, you know, even a factor of 2 or 3 is something that is sometimes not sustainable, because you know your databases are really large, and why should I use so much? Because space is there, the space, we have to live with the space, you know, we can't, it is not pre-processing time that we encounter once and forget. Okay. So, it is certainly an issue. So, we will see what to do about that. Okay, maybe I will just leave you with some more thoughts. So, this was about, and okay, so this data structure, where I have a primary data structure on the x coordinates, and I have a nested data structure in this. Okay. So, this is basically the range tree. Okay. So, this is the range tree. So, I will just write it here. So, a range tree, say it is 2 dimensional range tree, let us say. Where the primary tree is built on x coordinates and within each node we have and here we just observe that query time is order log square n plus k, space is order n log n. What happens, you know, if you go to higher dimensions? Can you extend this scheme? So, suppose I go to 3 dimensions. Okay. Now, I have a box. Okay. I build a primary data structure, let us say on, so what is this, you know, so y x z or something like that, right. So, I build something on the z, the primary data structure. Again, there are only 2 log n canonical intervals. Now, each of these canonical intervals is what? Is a 2-dimensional data structure. So, inside the node there will be a 2-dimensional data structure, right. And so, this extends to any dimension. Of course, you have to analyze what kind of query time will be there and what kind of space requirement will be there. But in principle, this is a simple extension, but you are going to certainly pay in terms of something in space and something in query time. It's not going to be log square n, it will be probably higher. So that's a good case. In k dimensions, probably about close to about log to the power k in query, and about maybe a log to the power k and extra in space, but one has to rigorously prove that. Right? Okay, so this is about range trees and higher dimensional range trees. Coming back to this problem again, so I am scratching it lots of times. So my final thing is again y1 comma infinity, three-sided. So one side, sorry, just a one dimensional range query was log in time. Okay, two dimensional range query, at least in the way that we have described it today, it's log square n. Will life be any simpler with a three-sided query? This is called a three-sided query. So this is something that we'll take up in the next class.